Okay, then should I start? Then, welcome back to Heuer, who will speak about p-adic non-abelian Hodge theory via Moduli. Yes, so thank you very much for being here. So I want to talk a bit about how, in this talk, about how moduli spaces can be used to reorganize speak of p-adic non-abelian Hodge theory. Okay, and I would like to start by reminding you of the setup, which is the same as setup of the talk I gave on Monday, but I was advised to see that everybody still remembers everything from that talk. So the setup is the p-adic ones. We have isoprivate flows, and p-adic can be qp. P-adic can be lattice. In particular, it's a geometric setup. So for purposes of time, they can be same. And for the beginning, we can work with any smooth proper Euclidean space of C. So maybe I was working with a smooth projective space on Monday, but in fact, I will later in the talk restrict attention to the case of curves, for which this is already very interesting. Okay, and so remind you that the goal of this area is it's formulated in its first form to be a continuous representation of the five-dimensional group of the pro-finite group on finite dimensional C vector spaces, so continuous representations of this form. And so when I talk on Monday, I explained that it's related to the study of pro-étale vector bundles. And I also explained, or well, actually I didn't explain, I have just mentioned it, that currently we could consider vector bundles at a larger size called the V topology, and so this might seem a bit strange, but on Monday I worked in this category, and there was a good technical reason for this. And today we need to work in this category. There's also a good technical reason for this, but I won't explain the technical reason. Okay, so you can just treat these two things interchangeably. And today I will want to work in D vector bundles. Roughly speaking, this gives me some more building to make constructions. Okay, so roughly the way that this worked was that to a representation, we can formulate is some kind of like a local system, and then we can tensor this with a structure sheet in order to obtain vector bundle on these sides. Or the way I presented it on Monday, one can take a Riemann-Hilbert correspondence type of perspective where we consider some universal cover, and then regard this as the Galois group of this cover, and then regard this representation as the descent data for a vector. And since this cover is a cover in pro-étale or V topology, the vector bundle will be given this way, this vector bundle. Okay. And so I want to now recall the main theorem of my talk on Monday, which is supposed to do precisely this. Let me explain these categories here. And the statement was as follows. So this was the p-adic Simpson correspondence. This is the name. And it depended on two choices. First was certain lift, do some pre-filtering. This is a typical datum in p-adic function theory. We know exactly what it means. It's related to Hodge statistics. And in an arbitrary situation where this smooth probability space comes from, for example, some discrete value field with a quadratic field, or even some finite extension of QP, then it cannot be such. So this choice here is non-fair. It's okay. It's a good reason why it's there. And then there was a second choice. This was the dating of an p-adic exponential. Namely, a continuous splitting of the logarithm. And perhaps one could also ask that on the convergence radius of the exponential series, it does what it should do, but in fact, this is not even necessary. I mean, in order to get all necessary relevant compatibilities to other theories, this is of course something one wants to ask, but yeah, any such function would be okay for the statement of the theorem. Okay, and the statement is then that these choices induce an equivalence of categories. Oops. Equivalence of categories. On this requirements. The speech topology and the category expands. Next, and the way I want to think about this is that this is the category we want to understand, which is very, very mysterious, and in fact, locally this very mysterious. And this is the category of differential data, linear algebra data, arguably that we understand much better. This is what we can do now. And then just to bring these representations again into the picture. The function of continuous representation of the half-unrelated group of finite and see of the places fitting fully faithfully into this category, so that we can ask what the essential image in Higgs bundle is, and also just reporting from my talk on Monday. If we follow some further conditions, for example, if this is a curve over CP, the completion of an branch closure of C, we can hope that here we can impose the same condition as in the complex non-abelian Hodge theory, namely that the Higgs bundle will be semi-stable with vanishing gradually determined passes, but in general, it's known that the story is a little bit more. Okay, now, so this theorem, gives a categorical description of the vector bundle is an X candle equivalence and so on. So that's very nice. So in this sense, it achieves this goal of describing this category. But there are a few things which are well, a little bit strange about it, perhaps. Right? The first is this point of an exponential, which does not look like natural at all. There's no canonical such thing. It's a weird datum. It's not a geometric datum. For example, if I extend base fields, which I don't know, we sometimes have to do in, especially in the p-adic setup, not etc. Then I need to choose a new exponential. And so this is not something which is somehow compatible after base change. So that's weird. And something which is not in the picture is that usually when I write down such an equivalence, we expect that it has good naturality properties with respect to morphisms of smooth properties. But in this setting, naturality is actually extremely subtle. And okay, so there's actually three different kinds of issues, and I won't mention them, but there's something to be said about it. So if I just write down the usual pullback functors, then in fact it won't be usually natural. Instead of some first of all some other functor, which is called by Daxin Xu pullback, which one can sort of explain. But I don't know, there's some subtleties around naturality. That's the main thing I want to say. Yes.
So, are these subtleties explained in at least one of you?
Yes. In the one which in which this correspondence is proved.
And I can explain it to study.
No, no, sorry.
Okay, so should I look? Should we look into the paper which called
With
smooth proper?
Simpson correspondence for smooth proper, which I think is
So it's the paper in which proved your theory. And in the same paper to explain in what sense this
yes. So, but I mean, for now, don't worry too much about the naturality. This is a little bit of a footnote. I mean, already explaining this exponential here is something which requires some further explanation of this exponential means. Okay, and these two things I mentioned are two motivations for what I want to do in this talk, namely, I want to explain first of all moduli spaces. p-adic analytic moduli spaces for all objects in this diagram. For categories in this diagram. And then the second goal is to use them in order to explain in a geometric fashion the appearance of the exponential. Okay. So that's at least for the purpose of this talk the main motivation for the passage. But I should point out that there are other reasons why this is a good thing to study moduli spaces for these objects. The first thing is already in the case of line bundles, in order to understand what happened, so in the case of line bundles, this diagram is completely understood. In particular, I know what I need to write here. And the answer uses moduli spaces in an essential way. So last time I explained that the condition was that the bundle here has an underlying bundle, the underlying line bundle of the Higgs bundle in this case is topologically tall. This is a topological condition which comes from the geometry of the moduli spaces. Okay. So with that all being said, we also it just happens that these moduli spaces have a very moduli spaces have a very nice geometric structure. Okay, so in order to explain what these moduli spaces are, we should first explain what geometric language we use in order to for moduli spaces. Yeah.
One question. I1 here is the I1.
No. Oh, yeah, that's a good question. No, it's the I1 in the sense of the Galois categories for the category of connected finite time couples. If you do the Young, then something weird happens, and you don't get Higgs bundles anymore. The Young fundamental group is too big.
Okay. So I think.
Right. So already in the case of line bundles, and you can ask what the characters are of these things, right? And you see that. So let's say we take curve, then there's a factor of z appearing in the de Jong fundamental group, right? And so the representation variety requires a copy of gn. Okay, and then we'll have a problem because you can't apply the logarithm to that anymore. And for this reason, it's actually you can't expect to have the relation Higgs bundles in this case anymore. I would be interested to see if there's still a way of doing this, but I'm not even sure if if I should expect the category of representation of the de Jong fundamental group to have some nice linear algebra description. I would expect it's rather large. It's very big. So in particular, if we had an algebraic setting, which you might just assume, like some smooth projective space, then this is just the usual p-adic fundamental group of standard. And later for curves, we talk about the usual fundamental group of curves. Okay. Okay, so I have a moduli spaces of Higgs bundles and I have a moduli spaces of E-vector bundles. Okay, for moduli spaces of Higgs bundles, there's a very well understood picture, right? We have some nice algebraic spectrums in the algebraic perspective, and I can just analytically this in some sense, yeah, maybe a couple of rigid spaces instead of objects or something like this to get an analytic theory. I will recall a little bit about this later, but here it's not so clear what to take. Okay, and it turns out that what we should do. The main question is, I want to take some function of points and write down some stacks, and what's the test category I should choose? And I want to explain that the correct category are perfected spaces. Or actually, I don't want to explain too much about that, but it's definitely the right choice. And okay, I give somebody the choice. And this is so far some category, and we start with the topology. Namely the B topology. Okay, so this is the topology which was already built into this category here. Okay, so maybe now's a good point to recall what it looks like. Namely, it's surprisingly simple. So the cover in this category is the family morphisms between affinoid perfected spaces, such that but for every quasi-compact open P, there's a finite collection of indices with quasi-compact open subsets such that sorry, easy one. Of course, these names. So this is the cover if it's a set theoretic cover. Okay, and then there's this QC condition. Okay, so this is exactly the same condition that you encounter in the definition of the FPQC topology. Okay, and then there's some condition that is a set theoretic cover, but there is in this setting no assumption, no algebraic assumption, like for example, that this morphism is faithfully flat in any way. Okay, so the way that I like to explain this is that this is like FPQC, which is usually the finest topology we can consider, but without the FP. Okay, it's just a QC topology. And well, it's somehow the magic of perfected spaces, and this thing is useful.
Does the letter D in topology have any meaning?
So this is for valuation topology. And well, what's the valuations here? This is a statement about the equality here because we're talking about adic spaces. So the points of these adic spaces are valuations. So it's a valuation theoretic cover in some sense. Hence the name. Okay. So the idea is we consider families of E-vector bundles and Higgs bundles which are parameterized and are perfected spaces. And in order for this to make sense, okay, it's clear what this means is I want V-vector bundles or Higgs bundles on the product of this form. Okay, I can make sense of this as an adic space. It's tricky and everything. And for V-vector bundles, it's clear what this means. Yeah, this is a collection of vector bundles for every perfected space testing this object. For Higgs bundle, there's a differential appearing. Okay, so it's not so clear what the differential of the space should be. Okay, And there's a quick lead differential. There's a quick solution and there's a conceptual solution. Okay, so I just mentioned the quick solution and then just say a few words about the the quick solution and then say a few words about the conceptual solution. So consider the first projection and define the differentials on this guy to be the full vector. So what we are postulating here is that perfectly spaces don't contribute to the differentials in some way. And usually you want to have
So they have zero potential.
yes, exactly. That's a good heuristic to keep in mind. Perfected space has zero potential. That's next to and so another way to think about this. So we're trying to do non-abelian Hodge theory here. So this is in particular supposed to be some kind of generalization of Hodge theory, in particular of the Hodge-Tate comparison. And we can ask what something like a Hodge-Tate comparison would look like in families. Yeah, I would consider GA portals on such morphisms here. And for this, the important point why this is the correct definition is that if I consider the morphism, the projection of sets from the V topology to the étale topology, then the way that the differentials appeared in p-adic Hodge theory, or this idea of constructing the Hodge-Tate sequence or the Hodge-Tate vector sequence, it's that these are the differentials. And it turns out that in the situation, we see precisely the full vector differentials. Okay, so in other words, so even making a further leap, so to speak, it is even better to write down a category of objects which are smooth over the perfectoid space. I call these smoothzoid in my argument just because I need some word for it. Okay, and then for these smooth, so this is actually something relevant because this means that I can form Heuer products of smooth morphism with some perfectoid test objects. Yeah, so the thing that I would get as the Heuer product is then would be a smoothzoid space. Okay, and this is something that comes up, for example, when you try to prove like a relative version in families of, for example, the Hodge-Tate comparison isomorphism, right, of a smooth morphism. And this statement here is true in this generality. If I have such a smoothzoid space and consider the higher direct image of the structure sheet, then I get the full back of the relative differentials of this morphism. So, in other words, I think the good perspective of differentials is that you can take this as the homological definition of differentials whenever you're doing p-adic Hodge theory or relative p-adic Hodge theory. So that would be my perspective of differentials. Okay, and this is also the reason somehow why in what we're doing here, this is the correct sheet to the Higgs ones. So that's what we can do now. To take this stuff out of the way, you can write down the moduli objects and consider. So for this, I don't even need proper list, so I can take any smooth rigid space over C, and we should pick some rank in order to get nice moduli spaces. And we have defined functors fiber points. We define some moduli stacks. So the first one is always the easy one. This is even though it's the one that's harder to understand, it's easier to define. And the same with the perfected space, not perfected space of the C, to the throughput of V vector bundles of XT of rank N. And then you can now do the same This is the moduli stack Higgs bundle of rank n. Paper I use curly letters, but I don't think my writing is already quite curly, so it gets completely unreadable if I try to do a curly version of this. So to the category of Higgs bundles of rank n, where I can now say that the Higgs bundle is simply a pair consisting of a vector bundle in the étale topology together with the OX linear homomorphism valued in this sheet of differential pairs, satisfying the usual compatibility, condition. Okay, so the goal is to compare these two stacks now. If X is smooth and proper, we perhaps can this be upgraded to an equivalence of stacks? And what I want to explain is that the answer is no, these two stacks are not equivalent. Rather, one is a twist of the other over the Hitchin base. That's going to be the main theorem I want to explain, and I want to explain in the case of curves. And before we get there, there's one.
And just a moment, and I know to what extent I'm not literate for spaces. So if I know would is a rigid space determined by its to
Yeah, okay, that's a very relevant question in this context, and the answer is yes, if it has sufficient regularity conditions, and the concrete regularity condition is semi-normality, and this is implied by smooth. So in particular, since everything that we ever do in this context is smooth, it is remembered by this. Okay, now if we talk about moduli spaces, then we might expect some singularities, of course. And I guess in some sense that in my perspective it's well, it involves some kind of regularization. I mean, it's passage. It can't distinguish between a rigid space and its semi-normalization. But so I will explain that in the situation.
For instance, it doesn't feel the nilpotence. So if
That's right.
So in other words, so there is a similar and maybe more familiar story from schemes and constraints. This supposedly not only perfect value.
Right.
Perfect means perfect means. Then and suppose we'll have a, let's say, scheme. We know the perfect value. Then probably we are saying then this means that we know the scheme up to universal formula.
That's right. Yes.
For instance, we don't see the difference between if the scheme is not used, we don't see the difference between we don't see the difference between y squared equals x cubed. So we have the single square y squared equals x cubed, which is and the credits normalization, which is yes, there is the different from the normalization. It's a universal formula. But only in the perfect you don't see the difference. So then the curve y squared equals. Can you say that here we have the function?
Right. I mean, so I would say that the passage from so what we're doing here, I didn't say the word, but what we're doing is we consider the passage from the rigid space to the associated diamond. The diamond is the object we just had by the vector spaces. And this passage is lossy, as you described, because, for example, we use reduced this. But I would say that in characteristic 0, it's much less lossy than the passage from scheme to its perfection. Yeah,
of course. But still, we don't see the difference between between y squared scheme and the final.
It is true. So, I mean, I would say that by going back a step back, we want to understand the category of B-vector bundles. So we have put ourselves in this diamond time framework anyway, testing by vector spaces. Yeah, so from this perspective, it's reasonable to keep this diamond time setting, by which I mean testing by vectors. But it is true that on the other side, for the Higgs bundles, we lose some singularities of the moduli space by doing this step. It is possible, probably, to find a.
Do you think that this is just the temporary state of the art, or that it's good? So is it? Of course, you cannot know for sure, but you probably have some intuition. Is that what is the natural structure? Is there should the spaces were considered really defined as rigid spaces only the corresponding diamonds?
So, okay, I mean, I guess there's answers on different levels. So, for the kind of thing we're doing here, this is a simplification step, which I think is permissible because it shows already the nature of these moduli spaces that we want to describe. We could work harder and test by more general things, like, I mean, there's nothing that stops us testing, for example, by general p-adic spaces or something like this. But then we need to be more careful already with the definition of the objects we consider here. Yeah, like, for example, we can impose artificially a condition that here we consider we don't consider contribution. Okay, so here we just need to say that we consider the structure sheaf. The differential is pulled back from X. But in order to not cause an accident here, we need to somehow impose the kind of condition that there's no non-trivial contribution of B-vector bundles on this component. Okay, and this is something that perfectoid spaces do automatically because for perfectoid spaces, étale vector bundles and B-vector bundles are the same. Okay, and generally it's good to test by perfectoid spaces because okay, this might sound like an empty slogan, but it is. I think very good thing to keep in mind that perfectoid spaces are trivial p-adic Hodge theory. Okay, this is a part of it. This generalizes in some sense the statement that B-vector bundles are the same as étale vector bundles. Okay, because in some sense this is saying that you always have such an equivalence here because the differentials are zero, so a Higgs bundle is just the same as a vector bundle. There's no. You could also, if you want, test by rigid spaces and still get a meaningful theory. This is in particular be enough to recover all the singularities of the algebraic stack of Higgs bundles. Okay, but I think I stick by my choice. I think for the kind of thing I want to say, this is a good test category all the time. It is, for example,
Oh, well, I didn't understand something you were saying. So when you said that bund for bund v comma n, do you say that if you want to evaluate it on, so you define it on perfectoid spaces, but if you wanted to evaluate it on a rigid space, like a super rigid space, then were you saying that you would have to modify the definition?
So at least in order to hope to have any kind of comparison between the two things. Oh, right. I mean, already for if we take the trigger, the point, X to be the point, right? And if we ask for a comparison between these two spaces, then this would mean to ask for a comparison between, well, Higgs bundles on Y and B-vector bundles on Y, which we do not have unless there's any kind of properness assumption, and already in this case it is kind of difficult. Okay, so testing by perfectoid spaces is reasonable because there we know that for the point the statement is true, roughly. Okay, but there's a way to salvage it if by well, one can make this explicit, but okay, let me maybe keep it as vague as saying that the vector bundle is fiber-wise trivial if I test at geometric points of X. Okay. Yes.
So there is a notion of arc in B stack.
Okay.
So are those stacks arc in?
I believe so. There's actually one thing that probably just my ignorance. There's a separatedness assumption in the definition of charts for arc in B stack, which is not there for the algebraic stacks. So this guy, for example, is the diamondification of an algebraic stack. So it an Artin stack, sorry, so it should rather be an Artin V stack, but right. Also, because we can eventually compare these, but only after the fact. So this is not at all a priori here. But that brings me to something I would like to say now, and because there's one thing we should one second, that's okay. One thing that we should already say, okay, which is much weaker than being an Artin V stack. So by the way, I mean it doesn't matter so much what these words mean. Yes, these are yeah, in some sense, smallness assumptions that you can. I mean, these stacks are a huge category, and these somehow tell you that these are more manageable and so on, like algebraic stacks. And one thing that we can say, and this is a very non-trivial theorem, is that it's. I was talking about stacks all the time. It is not at all clear that this definition gets to be a stack. And the problem being that there's an p-adic underlying Higgs bundle, but I want to have descent with respect to V covers in the variable T. Okay, but this turns out to be okay. So then the M and Higgs and okay, and then there's at least one technical thing one can say they are small these steps. And this is enough to say that
what does small mean?
Technically it means that you have a cover by a perfected space. And in effect, it means that this is, for example, you have access to things like a topological space associated to these objects. So at this point, it would already make sense to ask whether I have a homomorphism between the topological spaces associated with these.
Yeah, I was just going to ask, in your definition, you didn't ask if X be proper. Is that kind of a deliberate choice? I mean, in the end,
oh, right. Okay, sorry. So when I said that these things are Artin stacks and so on, I was thinking about the proper case. So I can only hope that these two things are like reasonably nice.
But this theorem is true enough.
This is always true.
Yeah.
Yes. So we've already told you that. I mean, smallness on the perfectuate world is still pretty big. Okay. Okay. So, so this part, for this space here, by the way, it is the stack property that's hard to improve. And on this stack, it's the smallness which you have to work. Okay, but for now, I just want this to mean that they are reasonable geometric objects. For example, you can say that you have an entire morphism over such a thing. Okay, so the next thing I want to discuss is now I actually want to do geometry with these things. Okay. And I want to talk about Hitchin maps. And for this, you should assume that it's a proper. It's this means, of course. And so on the Higgs side, the Hitchin morphism is construction in classical construction in algebraic geometry. I'll very briefly describe. With a little bit, namely, this is now a morphism of V stacks. And I want to note curly H for Hitchin. Okay, and it goes from the correspondence of rank n to the Hitchin base of rank n, curly A. And this is just an affine space. This was, by the way, the reason why I need to assume proper here. That's at least I can still write some V here in general. Okay, and there's an affine space associated to this C vector space here. This is the ith granite bit of the symmetric algebra of the differentials on X. And it's given by sending a Higgs bundle to the characteristic polynomial of theta. Well, the only way that makes sense. For example, by choosing some local coordinates or something, or perhaps by thinking about it as the morphism after extending the ring structure to omega.
like this. Okay, so roughly speaking, for example, after choosing some basis of omega, what you're doing here is expressing it in terms of endomorphisms, and then just remembering the characteristic polynomials. And then this is a spectral data. So that's very true to say. And right, so before I go to curves and recall what this thing looks like for curves. So I mean, this is a classical morphism in algebraic geometry, which people study because its geometry is very interesting and in higher dimension at least not completely understood. Okay, and we can now first of all make sense of it as a morphism of these stacks. But the nice thing and the very surprising thing from the point of view of complex geometry is that it turns out that there's an analog of this morphism on the V vector bundles. Okay, and that's the next thing I want to explain on. And when I feel a lot, I can have say that.
So in complex geometry, we don't have a direct analog of P vector.
Right, at least as far as
The naive analogy wouldn't go for a while. We have even if there is an analog, we wouldn't just take it, right? So
Yes, you're right. So in this sense, my statement that there's no analog in complex geometry didn't make sense. But the good thing is that, so I didn't say this yet, but inside of the stack of V vector bundle, we have the stack of representations. And I mean, this is covered by some representation variety, which is some actual rigid space you can write down. And since this is also a rigid space, this means that I can, at least in terms of representations, think of this morphism as being a morphism of rigid spaces. And for this, I have an analogous, question, let's say, in complex geometry. Now I can write down the representation variety. I can go through the Simpson correspondence and then the Hitchin fibration. And this gives me, well, at least a morphism of sets, first of all, from the C points of the representation variety to the Hitchin base. But this is not complex analytic, even in the case of line bundles. I think I gave an example on Monday that shows this. Right, but the fact that on this side it turns out to be a morphism of rigid spaces means that something
so
works
it's
better.
better not to, at least at this stage, it's better to forget complex.
Yeah, maybe.
We are in the, we live in the p-adic world, we forget all.
Exactly, because if we think about complex geometry at this point, the maximum we might be discouraged in trying I want to try next. Okay, so that's different. So the goal is I want to construct a morphism from the stack of V vector bundles to Hitchin base. And there are several constructions of this now, I guess, which
Are
they are all equivalent. Yes. And the one I want to represent is, so they both use the local p-adic Simpson correspondence in some way. And I don't want to explain what the local p-adic Simpson correspondence is, because for this I would have to introduce some technical terms. And the idea is roughly that V vector bundles and Higgs bundles become equivalent to each other locally on X if I impose some assumptions that the objects are p-adically close to zero. And what this means in this case is that I can take a V vector bundle, I can localize, pass to a Higgs bundle, and consider the Hitchin image of this object. And the non-trivial fact that one can prove is that this construction glues. Okay, that is essentially the proof I gave in my first article on the subject. But there's a second construction that I want to just equivalent. I mean, also in the sense that you can, like, after some work, say that it's basically the same proof, but it gives an additional interesting object, and that goes by the name perhaps of geometric sense theory. Maybe I want to explain the result of p-adic and one give us one. Maybe the setup is slightly different, so we give a like extension of it. Maybe because we want something that works on these smoother spaces, but let's not worry about this too much.
One is where one was here.
Yes, exactly. That's Louis Pan of yeah, the University of Chicago. Now we make a choice. Let's say so. Let's see what I want to add. Not want to talk about two, but let's just take explicitly this object here, which is the fact. Okay, and I want to phrase this theorem in a rather weak form, which is already interesting. It says that we can attach to any v vector bundle. There's no problem with RT here, by the way, if you don't want to. Any v vector bundle V, a canonical Higgs field.
It's not well, it wasn't V or Y, so
Yes, I know this is Y, and the v vector bundle V is on Y. I mean, perhaps it's easiest to first read the theorem without observability, okay, and then the statement is just that there's a version of it in the vector effects. Okay, but maybe that's the best way to think about it. And the claim is that one can attach to any v vector bundle canonical Higgs field called the canonical Higgs field. Okay, so this is now the morphism of v vector bundles, but of course the definition of Higgs field still makes sense. Yeah, it's still for some commutativity. And the statement is that this is functorial V and natural in Y. Okay. And one can now give a unique characterization of this Higgs field here in terms of the local p-adic correspondence. But instead, I want to just say the following. Well, at this point, this would be the trivial Higgs field, right? But one can say that one can attach it in such a way that this Higgs field is zero if and only if V is a trivial locally with respect to the time topology. Okay, so any étale vector bundle defines the V vector bundle by Hodge, right? That was Hodge control from vector bundles in the étale topology to vector bundles in the Hitchin topology. And the statement was that they don't agree. And now, in some sense, there's this quantity which measures the failure for this descent. Okay, and so Mark was the first to explain to me that you can think of this as, in a concrete way, an analog of a p curvature in characteristic P. And maybe a slightly looser analogy is that, well, starting from representation, right, is analogy with the Riemann-Hilbert correspondence, right? That in complex geometry, that then you start with the representation and then you associate with the vector, which gets an additional data, namely a connection. And the feature of p-adic situation is that instead the representation we can associate a p vector bundle together with the Higgs field. And I really can't explain why in theory chemistry we get the Higgs field rather than connection. Just a feature. Yeah.
So is it the defining property that if we expose those conditions that we want functoriality in V, naturality in Y, and also the state that equal to zero, we have this triple.
This is not.
So is that is determined?
No, this is not unique characterization. I mean, I could just scale the Higgs field, right? But I mean, I can perhaps very briefly.
Well, sense.
Right. So there's an additional statement here, which I want to speak on the record, but let me mention it in this little space here. Okay. So if we assume the local Simpson correspondence, this says that étale locally on Y, we can associate to the Higgs bundle under some additional choices of what is called the toric charge on Y. And the statement is that, so I can make sense of the Higgs field. This is not slightly confusing, but I can write down the following diagram. It is completely topological. okay, and which said that amount theta computes with itself. Okay? Yeah. And now I can say that the commutativity of this diagram means that theta itself is a morphism of Higgs bundles. And now I map it through the category equivalence and inherit a Higgs bundle of V. And the non-trivial fact that one needs to prove is that this does not depend on the choices going into the local Simpson correspondence. I mean, and I think Heuer was the first one to realize this. So, yes, I was not at all aware on the p-adic Simpson side of this constructions. That's constructions. Right. So after, so my calculator is very precise, right? And then it is in a local factorization. And then if I also say that everything is natural in X, then it gives you the characteristic. This is the characterization you give in our argument. Okay, but now this means that I have an operator which I can consider the associated spectral data. Hence, I can define a Hitchin morphism for the data. So, I'll make this precise. Oh, let's speed up. And by the way, one thing. So we can say perhaps this. And all of this so far works more generally not only for vector bundles, but for forces of any reductance group. And in fact, it is a slightly weird feature of the situation that I don't need to assume that the group G is algebraic. I can take any rigid group. These Hitchin morphisms exist for any rigid. And to explain what the Higgs field, like what the general G expanded is for the general group of this one. Okay, so we can now add a desired analog of Hitchin morphism. What do you about this? And okay, so in anticipation of the main theorem,
So anyway, the important thing is that this is the quite non-trivial theorem, and you didn't think.
that is correct. I gave some hints.
We have to believe.
Yes, I'm afraid. But so the main input that goes into this is in any case the local p-adic Simpson correspondence. And to spare you some technicalities, I did expect local p-adic Simpson. There's another way of which is perhaps a little bit easier to explain of how it's Moduli constructed. Namely, something I mentioned on Monday. If we consider for this object y the morphism from the V side to the entire side, we can describe the higher direct images of GLN. And this turns out to be the matrix of the V group of this vector group. And that with the differentials, Higgs field condition, inverted out by the direction. So what you can think of this as being the sheaf of isomorphism classes of Higgs bundles and this is the canonical isomorphism. And so what this means is I can associate to vector bundle its class in this sheaf. This particle isomorphism class is a sheaf bundle. And then I go to the other side, and here it makes sense to take the characteristic polynomial again. And this way, perhaps a slightly more direct way of constructing without using this thing morphism to the Hitchin space. This is how I do it in my first article. But in any case, essentially the construction is the same. Both have a close relation to local p-adic Simpson correspondence with the defined. If we're only interested in the proper case, then I guess after the fact you could characterize this thing by saying that instead you take the global p-adic Simpson correspondence. Okay, and then you can associate your vector bundle, a Higgs bundle for the global correspondence, and then take the associated Hitchin image, and then the statement is that this glues, like in infinite, right? But this is a canonical factorization at least. Okay, let's basically write down more and set it now. And right, and anticipation human theory, I want to call this the twisted Hitchin morphism. This is the same Hitchin space as before, and the vector bundle, the characteristic polynomial of the canonical scale of this is. Okay, so when we now in a more precise way, what we're going to be, we want to geometrize and the p-adic Simpson correspondence. This data set as a comparison in geometric sense of these two states. Okay. Yeah, sorry.
So we have this result on the first we have to show the gel, and so that's also generalized.
Relative group.
Yeah, right.
Yes, in fact, to any relative group. And I can tell you exactly what the difference is. So yeah, I mean it's exactly what you would guess. So you take the diagram and then push out by the editor. Right. And in fact, this is now a generalization of the statement, which is not important because I just erased it, because you can take GA here. And then here you get the differentials. Yeah, so this is a non-abelian generalization of this local computation. This statement. Yeah. That's a non-trivial statement because this is the statement that for any relative group G forces on perfected spaces agree in the étale. In the étale algorithm. And this is actually like a companion paper of this article on moduli spaces. Yeah, I mean, just proving the factor differentiation of the vector spaces requires already some. Okay, so this is the cryptography of the Okay, so and so this is something which I think can be done in general. It would be nice if in the case of curve. So I want to now wrap up this block. Let's assume. So let's assume that X is just the smooth projective. And this is now about joint work with something. And how I can focus. Okay, so first of all, in this case, we can put something which would be true generally, which immediately clear, namely that this morphism here is obtained from the algebraic morphism, from the algebraic stack of Higgs bundles to the algebraic Hitchin base. In the only possible way. And this only possible way is called diamagnification. Of Hitchin morphism in algebraic sets. So what this means is I can really think of this thing here on the right as a classical object. Diamonification roughly means that, I mean, these are algebraic stacks, I can test them on rings, and what I do is I just forget the topology. I just take my perfected algebra and stick it into the algebraic stack.
Gentle. So, when you say Hitchin morphisms in algebraic, so H and H tilde are both Hitchin.
Yeah, maybe one is called the twisted Hitchin morphism or something.
And twisted Hitchin is H tilde.
Yes, yes.
Which is the diamond definition. What does it mean? So there are. I understand. I don't have to understand what diamondification means at this point. But when you say Hitchin morphism in algebraic, so you are algebraic as opposed to analytic.
Yes. So let me write Higgs and alg for. I mean, okay, sorry. We are using here, of course, that this curve admits the canonical algebraization, so it makes sense to speak of it as a scheme. In this case, I can attach to X an algebraic stack of Higgs bundles, and I can evaluate this as R as an algebra, so an abstract algebra forgetting the topology. Okay, and I'm afraid this statement, as I wrote it, well, okay, so again, what we proved is only that.
So you will assume that X is the curve that we hold. Is it really necessary? For instance, does this theorem prove that X is the curve?
Our proof uses that X is a curve, yes, but and actually we proved something slightly different, and we only proved this after stackification. Additional stackification step involved. Okay, I mean this is kind of okay, because of course the theoretical topology here is much coarser than the V topology on the side, so a priori we need to do stackification. But Peter Scholze informs me that neither is the stackification step necessary nor the curve assumption. He thinks he knows how to prove this using his joint work with Clausen in good generation.
Sorry, so those algebraic stacks, Higgs, are they for Zariski?
And so on the one side, we don't have any Zariski thing. And in fact, one can easily show that this doesn't come from this. Even in the case of line bundles. But yes,
the topology of those algebraic stacks.
I mean, well, do I get to make it an algebraic stack? I guess take FPPF or something. But the statement is then that well, you still have a morphism of sides. And an unification induces a morphism of sides from the FPPF side of the algebra to the V side of the Don't be worried, should I be using protected? I think this makes sense.
And this is like literally the definition that if you're testing your, I guess, V stack on Heuer for power plus, which is probably that you're instead replacing swap power plus by spec just the curve.
I guess, yeah. I mean, it's really not a deep constructive diamonification. It's just writing out the only thing that makes sense in terms of some kind of analytification factor. I mean, it's the same thing. I call this diamonification because it's just the natural extension to algebraic stacks of what you do when you define an analytification for the. In general, I can associate to any scheme. First, maybe you'll find a type, let's say, it's an associated adic space, and then I can form the associated diamond. But I can also skip this step and just transform the scheme immediately to the associated diamond, and then I essentially this. And this is just the stack version of it. It's really some computing form, and there's no
I'm showing that smart comes as diamondification. The map onto the algebraic stacks means that like somehow that describe all equivalence relations.
And so what is this? It's an approximation without the Gaga. Okay. approximation in the sense that roughly this means that whenever I have an Higgs bundle which is on x times t, I can approximate it by something which is already of finite type. And then in the second step, I can say that so that it is still on a rigid space, and in the second step I say that it comes from the scheme. So and that's also the I guess the idea behind Scholz's strategy. This very general Gaga strategies he has to work with Daxin Xu applies in the set. Okay, so I'm putting this here to some. I mean actually, right. So in the case of curves, we would sort of see what is. Anyway, so I'm putting this here to tell you that this thing here is really something absolutely not boring. Yeah? It's the classical. I mean, I guess already for curves, Hitchin vibration is kind of interesting and non-trivial and so on, but it's really in essence the algebraic object. Nothing new that I get from classical space. Okay. So the next thing I want to explain is that on both sides, so classically, in the case of curves, there's a phenomenon called abelianization, which means that this here is a fibration in the abelians of abelian varieties. It's a very nice geometry. And I want to explain that there's an analog on the other side. So abelianization for p-vector.
Maybe we should.
Yes,
so we need
yes.
to-
Okay, and actually, now it's a good point, right? So then let's take a break now, and after the break, I will explain why both of these morphisms are generically proportional under some restricting of the Abelian brackets. Okay, so to the people on Zoom, this absolutely nothing. And okay, so we continue with right. So abelianization. This is supposed to be an explanation. First of all, let's have a classical description of the Hitchin morphism. So just to set up, just remind you it's not on the board anymore. This is now a smooth projective curve. And we need one further additional. The genus has to be equal to 1 for safety reasons that actually say greater than 1. Okay, so we have a Higgs bundle on X of rank n. And I mentioned on Monday, we can rewrite this morphism theta first as a morphism from the dual of the differentials in the morphisms of E. That is because every dual means that you get functional from the differentials and you can use this in the morphism. And then the commutativity condition means that this extends to a morphism of algebras from symmetric vector bundle. And by this, you can regard it, this bundle, the underlying vector bundle E, as a module on the symmetric algebra. So this is just to say geometrically that E now becomes a coherent sheaf on the cotangent bar. It's in fact perhaps a good description of what the Higgs bundle is anyway. But in fact, we can be slightly more precise. Or rather, we can cut down the algebra structure maybe by Katie Hamilton. Run out this already modules under the algebra before. Modulo the characteristic polynomial. It's slightly vague, but especially since we're on the curve, there's locally only one way to think. Size. Because locally this is just a polynomial algebra in one variable. Okay, and then let's observe, so this is just okay. This algebra here only depends on, well, first of all, it only depends on theta, not on E in some sense. But also, it only depends on the characteristic polynomial, and this is precisely the Hitchin image. Right, so it only depends on the image of an H bundle. So what this means is that somehow in fibers of the Hitchin pattern, you can regard the underlying bundle as a coherent sheet on what's called the spectral curve. For spectral curve, because it encodes the spectral data of theta. This is the finite pattern given by the relative spectrum of the algebra. And this only depends on this theta, in fact, only on the image and initials. So
this is the usual story.
yes, this is completely, you know all of it.
So this is not something specific for the analytic, for the non-Archimedean analytics.
Yes, maybe one non-trivial that's worth. And I mean, even non-trivial modulo everything when those statically about Hitchin fibrations, it now works with the vector families as well. So far, I was only taking a Higgs bundle on X, but now I want the same for a Higgs bundle on X times T, which is so the statement is that we can somehow assemble all these spectral curves to a relative curve. This is a finite flat cover. And the relative curve is now what I get by further composed to the Hitchin base. So this is a curve over the Hitchin base. Such that for any bundle, theta of rank n on X times T or T to the vector space, maybe F minus the vector. In regard the coherent module under the what we take now is then called this composition here pi. Sorry. This let's say push forward of the structure tree to here. So this is some coherent algebra. Push back to X times T for the morphism from T to the Hitchin base, which is determined by the Hitchin image. Okay, this looks a bit confusing when I first see that, but the idea is just that all these things I can see on points where it's just linear algebra can be assembled into its family. Okay. I should be slightly careful in saying coherent module on something highly non-Abelian, but we'll forget about the subject. Okay, and then why is this called abelianization? This is called abelianization because what we've done here is we've traded the non-commutative group GLN for a coherent commutative algebra, which somehow is now the module, which this thing is the module. And furthermore, you can say that in good situations, this even becomes an invertible module. So GM plus this goes by the name BNR correspondence, and this is now the version of it in the setting. And that's
What does BNR?
yes. Sorry, I mean, for the reason I'm saying is that's how people always refer to it. This is Profil. Simon, Hartmann. Okay, and this says that yes, there's a richly dense open locus. Which I'm going to denote by a sub over which, first of all, spectral curve becomes smooth. Ramanam, I forgot on that way. So this can have very bad singularities. In fact, if you look at the fiber over zero, it just becomes some highly non-reduced thing. But generically, under these terminologies, it becomes smooth. And then it's essentially a linear algebra effect, although I do have to be careful in the perfectories. I think there's something more trivial to say there. That's essentially the second part of the statement. So if I have an Higgs bundle set up as above that, such that its Hitchin image lies in this locus, which is called the regular locus, because of the smoothness here, then this module under this algebra, it becomes invertible. Okay, and by the way, so this means that I can recover the underlying bundle as the push forward of a line bundle along this morphism here. And I can also recover the Higgs field because this is encoded by the structure morphism I have from where is it? Exactly, structure morphism from Sim omega into this, which recovers Higgs field. So this is some that's the thing I can do. And what this means is that generically, this morphism becomes a relative Picard variety for this morphism for the spectral term, this morphism from Z to Hitchin base. Okay, and for what I want to do, it is important that in fact it's a slightly more general statement, namely what I can still do, even if this bundle here is not invertible, I can still twist it by invertible sheaves under this thing, just by tensoring and then pushing down. So what this means is as a natural canonical action of I'm going to write this a lot, so I'm abbreviated the relative Picard variety, okay, of the spectral curve on the Hitchin morphism. And again, as a second half over regular locus, this makes H into a split torso. In particular, this means, so to those of you who know this theorem, theory, the only non-trivial additional part that I've told you
is that this still works if I test by perfectors. Okay, which is not immediately clear because there's some algebra, relative algebra involved, but it's fine. Okay, but what this means is that even if I test by perfectors, over the regular locus, this guy here is represented by a smooth rigid space over the regular locus. Yeah, which is given by the relative Picard varieties. In particular, its fibers are disjoint unions of abelian varieties. Okay, so particular. Statement of this theorem is namely that this is Hitchin morphism, a vibration in disjoint unions of abelian varieties. Okay, and well, you can get what comes next. Namely, the same works in some sense in the beat point. However, yes.
So this even vibration, and this is over the regular locus.
Yes,
And
I mean,
then-
yes,
And the Picard variety is not abelian. The variety is not abelian.
that is also true. Yes, yeah, exactly. I mean, there's the two issues, right? I mean, first, the action isn't free anymore on the singular fibers, and also it's not an abelian variety anymore. Yeah, but you still get a meaningful action of this relative group. I guess it's not even representative.
Yeah, so it's just a statement that you can tensor coherent sheet by line bundles.
Yes, exactly. And now you could think that, you know, since everything works well so far, we'll just do the exact same thing on the V side, right? So basically what we hope is that you take the V vector bundle, which lives maybe here, right? Or on X.
So total, there was a statement that there is a similar story from Heuer.
Yes, I'm going to explain it. But first, I will explain what doesn't work. Okay? Namely, one could hope that it is true in general that if I take a V vector bundle here, then I can find maybe over the regular locus a line bundle, a V line bundle here. Okay, such that this vector bundle is pushed forward of this line bundle. Okay, and then I have a strategy for constructing the system correspondence, right? Because what I need to do now is I have a line bundle. For line bundles, I know what to do. I go from the V vector bundle to the associated Higgs bundle and then push down. Okay, so that was my strategy where I started looking at these things 2 years ago, and it doesn't work. Okay,
So the hope was that at least over the regular locus like this,
yes,
and turned out that this is not right.
but it's still useful as a strategy to keep in mind. Okay, the idea of, so once again, so what reorganization does is taking the Higgs bundle and then reducing it to something which is a line bundle, so something total under some abelian group over some relative object here. But for line bundles, we know what the Simpson correspondence looks like. I explained it on Monday. So one could hope we use it here, go to the other side of the correspondence, maybe to Higgs bundles, and then push down. And the problem with this is that this morphism is finite flat, it is not étale, and unfortunately, the push forward of a line bundle, the line bundle under a finite flat morphism is not a vector bundle anymore. Okay, there's some issues here, and they are serious. This is not some stupid technicality. But the
Just more. So you are saying that the problem is that push forward of the line bundle with respect to finite flat morphism is not a vector. So in algebraic geometry, it is a vector.
right, and the problem here is that if I have a morphism, maybe it looks like this, which is finite flat, and I set it by a factor object, and now I form fiber product, then very often, in fact, this is represented by an adic space, even by a factored space, but this morphism is no longer finite flat. So finiteness is not a good notion if you consider these large categories. Finite étale is, finite is not. Okay, but I'm mentioning this strategy, which doesn't work, because it still gives the right hint to what one should do. Okay, namely, what still works is I can still twist. So I'm in a relation for vector bundles, then I can bring the thing here, and then it can be done. So using the canonical Higgs field, of course.
we have analogous construction on the side. To some extent. Okay, so given p-adic command, now you can Higgs field make V into a module under the exact same algebra as before. These are the vector curves. And what I just explained is basically that what you're not allowed to do is take any invertible module for the V topology and twist this guy with that. But what still works is to take an invertible module in the étale topology. Okay, because then it roughly, I don't know, because this is étale locally trivial. I see that étale locally is isomorphic to my original thing, so it's still going to be kind of locally free. So what this means is for any invertible module, let's call it curly N. Can it make sense of this thing out here? Okay, and this is still going to be a d-vector bundle. And if I think a little bit about this construction of the canonical Higgs here, I see that I can compute a Hitchin image. And it doesn't change. Okay, because basically this is a local thing. It's local on X. So what this means now is that I've given you an action.
So just to reconcile what you said and what you wrote, this is an invertible. So kind of B theta means like somehow means risky or étale. I think this is implicit that it's étale or explicit.
Okay. Yes. So let's say it's an invertible V module in the étale topology. Yes. So on in étale. So to make this precise, in fact, what we should do, maybe I under the bracket is we take the push forward with respect to the étale topology, and then we pull back to the V side. That makes a difference. It's not the same as first pulling back to the V side and then pushing forward with respect to the étale topology. Sounds like technicality, it makes a difference. Anyway, so we can twist with étale modules. Such as étale line bundles on the spectral curve. And what this means is,
But if you replace your vertical, then you have to push.
Hmm?
If you replace.
no, I mean that's still different. Okay, so what this means first of all, like when we sketch data, is like the twisted Hitchin model still has a natural canonical action at the same relatively calm, right? Okay, and now we can state about our theorems. Fine. Now we have everything set up. So the first theorem is that in fact, over the regular locus, this makes the fifth vibration a p-torsor. Okay. Exactly as on
But I guess not split.
exactly. Yes, this is why I make the spaces.
Non-split.
Yeah, so there's no section. And this is something that you can see on this official picture there. Exactly the case. It's precisely what happens. Okay, and in particular, this means that we can reasonably say that this is somehow a vibration in the medium varieties. And again, but we can say something, maybe we can now really do p-adic Simpson in terms of moduli spaces. Okay, so for reason of time, let me skip one definition and just tell you. So that it exists. A canonical, so it exists for the function. If P possible L over the two ways. That is canonical and factorial isomorphism between the stack of p bundles and more curly. The twist of the moduli stack of Higgs bundles by this torso.
So here, the good news is that now we'll get a picture on the whole.
Yes, exactly. In fact, you can say some nice things about this thing over the regular locus, where it's perhaps even so. It's a principal reduction of structure group to the portion of this thing, and in this case, we can make sense of this as a constructible sheaf over the whole thing. Over the regular locus, it becomes locally closed, so perhaps even representative. So in particular, this goes to what Paul asked earlier, namely this gives us some handling of how big the space is, right? Because after an entire twist, it becomes symmetric.
But let's check, I mean, somehow this by all things like ban and L are sort of the same on the regular locus. That's Higgs, it's trivial. On the regular locus, right?
Yes, that's right.
But it's all built from the ban. Is it all built from the ban and then, or is it all made separately? I got you use.
So you mean how the thing is defined?
Yeah, or how do you build it on the structure?
Yes. Okay, so maybe I can write down one diagram, which explains it. Maybe this is the last thing I do because there's something about the exponential, right? So maybe I should give at least some indication what happens here. And okay, the one thing I need to just state is that in fact, I think like roughly remember what I was saying that so right now this P thing and also this L thing is still pretty large. Okay, and one can cut it down quite a bit. But for this one needs the additional datum of maybe around plus of size squared. And we can in fact a canonical up to this data construct a reduction of structure group of L to also under just the torsion part, and this is some relative group object, right? So I can consider its torsion, and this is like passing from an abelian variety to its associated p-divisible group. So this is much, much smaller. They notice by n of x. Okay, so in particular, since this thing here is constructible, this is somehow a constructible guy as well. And so in particular, this means that so just purely formally, what I got from this is immediate from the statement. I have now filled with a smaller sheet, okay, and now I can write down something which is actually not really a definition of this thing, but more a theorem about it. But in hindsight, I can take it as different. Okay? So perhaps maybe. So okay, let's denote the spectral curve. Yeah. And I want to consider its relative étale component. Okay, so this is going to be some local system, a ZP local system on here. Okay, I mean that's the classical thing if you want. Then there is a completing diagram. Where I take this local system and tensor it with the open unit disk. So both of these things are ZP modules. And then I consider the logarithm. GA. And then, okay, so something that I can't really explain now, but there's a canonical section of this guy here, which is related to the fact that there's a canonical differential on the cotangent sheaf. Okay, and there's a primitive comparison theorem that goes into this, so it takes some time to construct this morphism. But it's a feature of the situation that there's such a canonical section. And the statement is that this sheaf fits into a continuity diagram like this. Okay, and now we can say what the exponential does. The exponential is the fitting of the lower morphism on k points. Yeah. In particular, the exponential gives me, in some sense, a trivialization of this sponsor on sequence. Okay. And for example, one nice thing that I can buy with this is that after all this, I can say that as a corollary, if I take the sequence of the moduli spaces, then since I consider flex as a vector topology in that, that the Simpson correspondence in fact induces homeomorphism. Roughly because this morphism here is continuous, and therefore the splitting here is also continuous. And this, I don't know, if you remember the very first thing I said on Monday was that in complex geometry there's such a homeomorphism. And so in hindsight, we get an analog of this thing. But in fact, we get something much better, and we have the isomorphism between this. Okay, I think this, yeah, this is natural. Anyway, and we can do questions afterwards. So thanks very much for listening.
So why you said lambda was a local system of all of AN, but sometimes Z has some bad fibers, Z has some bad fibers. But nevertheless, this lambda is a local system over the whole base.
Sorry, no. It's sorry, I should be more careful. No, it's somehow whatever pro-constructible or something. Or
Yeah.
It's not a local system.
Yeah,
You're right. Yes, it's a local. Sorry, yes, it's a local system over the regular locus.
But somehow the LX works out to be. I see, but then the P is also kind of a bit strange on the bad locus too, and I guess. They're saying like the P is also kind of a bit nasty on the bad locus.
Yes.
Okay, so it all kind of balances out.
Right, exactly. It's consistent patterns.
Thank you.
One thing that you can still say is that since everything is trivial in fibers, we still get a non-trivial geometric statement that the fibers of these morphisms over the Hitchin base are canonically identified. And I actually wonder if this is an interesting statement even for the study of Hitchin fibration, for example, in higher dimension. Because I didn't talk about representations now really, but this morphism can make it reasonably explicit in terms of representations. So in principle, this could be used to study. I just had a basic question. So is it possible that there was a version of this result in the context of geometry over Oh yes. Okay, actually in my abstract, I think from this relation of complex and what geometry, and they didn't really materialize. I apologize. So this is the direct analog of the theorem of Daxin Xu in Moduli geometry, where instead you take the RAM one parameterizes vector bundle, and then I guess where this thing comes from is also a bit different, but the overall situation that you can express one space as a twist of the other is
so I think this is an important information because so the characteristic piece equation hopefully doesn't involve these
Right.
things but diamonds and so on. So something that can be now can you I think it would be helpful if you could first give some kind of more or less precise values.
The one in characteristic P.
And maybe you can formulate this.
Yes. Just check it out. If the correct reference, they are from two papers.
And also who are they?
Yes, sorry. I should also mention P-adic, who also proved a version of this. I think these two things came out at the same time. And the article is by you. The first name perhaps.
So Hitchin is worked here. Is it the chap who worked?
Embarrassingly, I don't know. Is it? Someone else?
Yeah, but Xu
I
was
think
the
so.
here and Xu
Yes.
and this somebody.
This is E8. That's my
Yes, but this is he worked.
yes. Then that's your colleague. And it is not a geometry required right versus accuracy. I should have guessed it right. First, P. And then they wrote a second article about geometric lengths and prime characteristic, which, considering the title of the seminar, I should probably say something about as well. But this is the one I think which proves a very similar statement. And this,
Yes, and well, we can of course look into this paper, but is it possible to formulate their statement?
So they consider the round set. And
when you say the round step,
right, so we have a smooth projected curve over FP bar, I suppose. And the round stack is the algebraic stack of vector bundles with flat connections on X. I shouldn't call this the round stack. This is the round modulus. Yeah. Space. It's a bit of a difference. And
the modular of the round locus, the round
vector bundles with flat connections.
vector bundles.
And then on the other side, okay, messed up my notation bit. In any case, I believe it is probably it's all about more moduli space, the different notations, but you can really think of it as being this. It's the same thing. So it's moduli space, moduli stack, a right moduli stack of Higgs quantum characteristics.
So we can, on the one hand, we consider that the bundle. So we are in a curve, so like connection.
Yes, correct.
Then you have the notion, but you have a notion. What has the notion of p-curvature? And this p-curvature gives you something like a Higgs field. Maybe here what has something. And therefore you get a Hitchin map.
Exactly.
From the
continuous
action
full length and total skyline. So I could write in 1 year, I think.
On the other hand, instead of vector bundles with connection, we can just consider usual.
That's right.
Then we'll also. So we have two. The only well. The curvatures probably expression form maybe not an X, but on X, which is here one has
right. So it's rather, I guess, the round step justified or
so we have two morphisms with the same base or more or less the same base. And now what is the claim?
There's an equivalence of specs between this twist of the drum spec to the Higgs moduli state, and now I need to twist it with the stack of splittings of the Atsumaya algebra given by the differential operators. So we can really give a complete modular interpretation of this thing.
Okay, just to tell how far is it from, let's say, from their idea was to think of so a vector bundle with a flat connection means you have a vector bundle with an action of the most naive way of differential equations. Now, August Vologodsky tell us one of their slogans, principles with the thing of differential operators is the bidimension of the center.
Right.
The center can be easily. So if we know this fact, then how far are we from the theorem of Chen and Xu?
And I think, we can go in the other direction. I think this is sort of a geometrization of this non-abelian Hodge correspondence and characteristic of August Vologodsky that I mentioned. And I guess.
Okay, this
Ah,
one,
right,
there's no problems.
right.
There's no problems.
There's no difference here. Yes.
There's no problem.
This- We are over curves here rather than over somewhat general, somewhat different situation. Probably also yes. And right. So I think it's in some way.
So anyway, so there are some non-trivial here, but we have to find. And now, are we? So, do you recommend understand? Are you saying that understanding the characteristic B story helps to understand your story?
Probably. Certainly, like conceptually, in the way that the objects are related to each other. In terms of the construction, I don't see it immediately, but people now tell me that it should be possible to have a concrete way of comparing these two things by way of some comparison of p-adic Simpson and Moduli Simpson correspondence. So it is really a good analogy, or rather, it's not only an analogy, but it can be more.
Where is the piece? Where is the end of the curvature?
The end of the p-curvature is exactly this curvature here. Because this is also what we use in order to define the Hitchin vibration of the other side. In the same way as you described, the morphism to the Hitchin base in this round and moduli base is after this twist given by the p-curvature. The morphism to the Hitchin base here is constructed using Moduli. And you have
Yes, but you didn't. I think you didn't feel it. Feel just don't from smart people. So, but now you are telling us that both their construction is somehow related to the motion.
Yes, I guess.
But but it's not very cool.
Well, I learned from Akil that one can make this reasonably technically precise in a way of concrete analogies in between the p-adic story and the Moduli story, right? Where roughly one thinks of the morphism from the D side to the étale side as being like this Frobenius twist. Yeah, right? Am I
think I don't know. Because there was supposed to be a Saki. Things I don't know that. So the peak curvature can be like sort of made geometric in the statement that the So the wrong stack of X, where X is a scheme for P, it maps that to the orbital to the Hodge stack. And the station maps to X, and it's a variable for that, for GX sharp. And it sounds like there's a version of the story in analytic stats where there's a replacement for the drama of Higgs stack that it's going to relate to these vector bundles.
Yes.
And it's going to be a jerk over the space set.
Right. And if I understand the abstract for Swagger Plus talk for next week correctly, then this is also something that they do this work with.
Yes, so next week there will be a workshop where part of will explain the construction. Well, the main, the main subject is Simpson.
Yes, and in fact,
Now the only thing is that I don't know whether I will be able to attend this workshop by Zoom because I received an invitation and I registered. So I don't know whether anybody can attend this. So, but maybe it will be eventually, maybe it will be. On the other hand, there is a chance that part of if more detailed symptom for us, the paper on this. If this is being around. Other computer operation.